think that we are a renewable power that people don't know much about. Some of that is what's beautiful about geothermal. It's beneath our feet. You don't see it. You're not taking up a lot of land use to develop it. We are sort of this one-stop shop for everything that one could need in the energy arena. I think it's a pretty exciting technology space for that reason.
This is EnergyCast, and I'm Jay Downhauer. Today we're talking about enhanced geothermal systems, taking all those hot rocks beneath our feet and putting them to work for us on the surface. Last year we spoke to the Geothermal Technologies Office, GTO. They had just released a comprehensive roadmap for the future of geothermal in this country, and it was hard to ignore. This one energy source could produce up to 60 gigawatts of new energy, more than 25-fold increase from the geothermal we use today. The key is bringing geothermal to areas where it's not already obvious. There were no Old Faithful showering tourists when I grew up in Louisiana, and until now, those geologically blessed corners of the globe were the only places that produced geothermal energy. But my guess says the work they are currently doing could mean that we could see geothermal powering the Bayou State or wherever you're from. They can do this, I'm told, by adding a little water and fracking the rocks just so. I spent a few years with fracking companies, so I was able to follow along with this conversation, I'm proud to say. For instance, we discussed how introducing water into the subsurface where it previously didn't exist can affect rocks below. Similar circumstance when I worked for a frack water recycling company. One of the selling points was that recycling the brine that comes up during natural gas production was better than fresh water because it did not affect the rocks below in the same way. My guest and I also discussed scaling challenges. Water in certain conditions will force subsurface rocks to precipitate minerals, which in turn can scale the pipes. During my oil and gas days, we formulated a few scale inhibitors, which we use in conjunction with the water we recycled. We'd bring these scaling chemicals out on an oil pad in totes on a flat deck trailer. When winter approached and the chemical was in danger of freezing, rather than install a bunch of heating pads, I talked to our experts about adding an antifreeze to the chemicals we were using. We tested the different batches in a downtown office freezer next to people's lunches. What's interesting is where the similarities begin and end between geothermal folks and my old oil and gas buddies. For one, frackers and the geothermal folks are targeting different kinds of rocks, as my guest will explain. There's also the matter of what each group wants out of their rocks. For one, it's a one-way express trip to the surface, the other, an indefinite round trip in the basement. But the potential to collaborate is unlike any other time, and the potential for geothermal energy has never been greater, whether for producing megawatts of power or helping a farm grow produce out of season. These hot rocks hold the potential to be our furnace of the future. My guest today is Lauren Boyd, Program Manager over Enhanced Geothermal Systems for the Department of Energy. In episode 62, we met Dr. Susan Ham with the Geothermal Technologies Office. They just released the GeoVision 2050 document I mentioned earlier. We also discussed a project out in Utah called FORGE, the Frontier Observatory for Research in Geothermal Energy. Lauren manages that program and helps design the direction enhanced geothermal will take, collaborating with researchers, universities, and small businesses to help chart the technology's future. I hope you enjoy my conversation with Lauren Boyd. We're here with Lauren Boyd, Enhanced Geothermal Systems Program Manager for the Department of Energy. And Lauren, we discussed the FORGE project with Susan Ham last year. Now the project is up and running. So what do you hope to accomplish out there?
What we're looking to do at the FORGE site, and FORGE stands for Frontier Observatory for Research in Geothermal Energy. Basically, this is our big opportunity in enhanced geothermal systems to test ideas and methods to bring enhanced geothermal systems to commercial reality. And just in case some of your listeners aren't familiar with EGS, basically these are engineered geothermal reservoirs where we have heat beneath us no matter where we go. But sometimes we don't necessarily have the ideal conditions for power production like we would in a naturally occurring hydrothermal system like you'd see at Yellowstone or somewhere out west. In the case of EGS, you might have a lot of stranded heat, but no fluid and not a lot of open pathways to conduct that fluid to the surface where you might see it bubbling up like you would at a geyser. With traditional geothermal, you're taking that hot fluid and we're producing power from it. And with enhanced geothermal systems, we're taking advantage of that stranded heat that's beneath our feet at tens of thousands of feet depth, and we are adding fluid to the subsurface, and then we're able to filter it through these permeable pathways, bring it up to the surface, and produce power. There's tremendous promise in EGS, which is why the FORGE initiative is so critically important, because it's really our big opportunity for revolutionary change in the geothermal sector to access this massive heat resource that's beneath the entire U.S. and, in fact, beneath all the continents.
EGS, enhanced geothermal systems. How much geothermal energy could we potentially realize if we applied EGS to what's out there?
We have a number of different laboratories and groups have done estimates, including the United States Geological Survey, the USGS, and our estimates are on the order of 100 to over 500 gigawatts of resource. And just for context, 100 gigawatts is equivalent to 100 million homes. And so that's the low end of the potential resource that we can access if we are able to advance the technologies, which is what we do here at the Department of Energy, to fully access that resource and see it come to commercial deployment.
And we're talking about base load energy. I mean, the earth never stops getting hot, unlike wind that sometimes doesn't blow. This is all the time, always on.
That's right. And I think, get ready to nerd out, but what I think is so exciting about geothermal energy is, yes, it's a base load renewable energy resource, which means exactly like you said, it's there 24 hours a day, 7 days a week, but it is heat that is coming from the interior of our planet, from planetary accretion, from radioactive decay of elements that were formed in the mantle, and from the crystallization of our outer core. And how many energy sources can you say are from these really exciting esoteric things? So basically, we have this massive kinetic energy that converted into heat in the center of our planet, and then this decay of these radioactive elements that's providing this constant heat source that is as renewable as it gets.
Yeah, one of the things that Sue brought up, I thought it was kind of funny, was she gets asked sometimes, well, if you use geothermal energy and you're taking heat out, are you cooling down the planet?
So on the order, no, at the level that we're extracting heat from, and especially if you think about a cross-section of the Earth, we're working in the very, very upper part of the upper crust. There's absolutely no impact whatsoever on this massive heat source that is the core and this radioactive decay that's occurring of uranium and thorium over time. So no, we're set for life.
Well, I segue into that because are there any things about geothermal you think the public just doesn't understand? And that was her answer.
Yeah, I think it's a great question. And from my perspective, I get less questions about the hazards, and I'm more just surprised and eager to help the community and the public understand the benefits of geothermal and how broadly beneficial it can be, what a diverse energy source it is, and how many different potential applications there are, from electricity generation to heating and cooling, industrial and agricultural processes. I think that we are a renewable power that people don't know much about, and that's generally what I'm surprised at when I'm having conversations with the public, and what we're really interested in trying to help change, to help everyone understand what the benefits of this technology are, from, as I said, electricity generation to heating and cooling. And I think the idea of utilizing a baseload energy source for your power production, but also to heat and cool your house, to potentially use for agricultural processes, for farming fish, drying paper, producing hydrogen if you wanted to. So we are sort of this one-stop shop for everything that one could need in the energy arena. I think it's a pretty exciting technology space for that reason.
Another thing I was curious about is whenever they talk about renewable energy, it's always wind and solar, and that's got to frustrate you too. Why is geothermal not looped in with wind and solar, and also hydroelectric? For some reason, it feels like they don't classify hydroelectric as renewable. Why do you think it's so hard for geothermal and hydroelectric especially to get into this club of cool kids, wind and solar?
Yeah, that's a great question. I've been here a while, and I am sometimes surprised to see that we're not mentioned alongside our sister programs. But I would say that our GeoVision study, which was released last year, has already shown such a tremendous impact on the recognition of geothermal as a renewable energy source. I think that things are changing in a positive way, and we're going to start tackling some of the barriers to people understanding what geothermal has to offer as a result of really exciting push of this GeoVision and the results. But To your question, I would say that inherently part of geothermal is an unseen resource. And some of that is what's beautiful about geothermal in that it's beneath our feet. You don't see it. You're not taking up a lot of land use to develop it, but that makes it inherently more challenging to understand. With the wind, we can see the wind blowing. We can measure how fast the wind is blowing and where it's blowing more. With solar, we can measure radiance. Everyone can see the sun, but people don't necessarily understand radioactive decay of uranium and thorium and latent heat that might be stored in the earth that's producing enough heat to produce power from. So I think that that's inherently a challenge, but more so the fact that it's beneath our feet and nobody necessarily knows it's there or why it's there. So we have that to overcome, but we're really excited about helping communicate what the benefits of geothermal are and why it's so unique and special now that we have the vision study to sort of cascade from.
And I'll certainly link the GeoVision document on this. Getting back to Forge, why Utah? Why this Utah site?
What we're hoping to do at Forge is try to tackle some of these big challenges that have been facing the EGS community, where we haven't necessarily had the funding and the risk appetite to tackle them. Forge is this opportunity for a field laboratory where the community can work together to try to resolve these challenges in this holistic and systematic way. And so these challenges are related to developing optimal fracture networks. So those permeable pathways I was talking about before for fluid to flow in, being able to prepare and design stimulations, which is how we open those fractures that carry the fluid. And then also knowing how to sustain a heat exchanger, which is our reservoir in the subsurface for a long period of time. And so Forge is aimed at solving those challenges with the community at a dedicated laboratory where we have more information than we've ever had before about a subsurface site. We started the process kicking off this initiative back in 2013 when we realized we need to solve this problem together. We can't be doing one-off projects, one-off laboratory-based R&D projects, research and development projects. This is a big challenge. It's a basic research challenge combined with an applied research challenge and an engineering challenge. It's a really awesome, exciting, big moonshot of a challenge. And working together is the best way to tackle it. The Forge effort is a 7-year field effort that was broken into a couple phases. We started with 5 projects and then ultimately down-selected to the Utah site. So to your question, the reason that the Utah site was selected was because it best fit the requirements that we set out initially in 2013 when we were designing the effort, and that was related to the characteristics of the site. It all comes down to what the geology is of the site, what the rocks are like, what the permeability, that's how fluid can flow in the subsurface in those rocks, the density of the fractures, and the orientations and the magnitudes of the stresses in the subsurface. And basically that just means how are the rocks going to fracture and how is permeability going to be generated when we try to create a reservoir. That's why stresses are really critically important. Basically, we were looking for a site with specific characteristics, a specific temperature range, 175 to 225 C, we wanted low permeability, meaning not a lot of open fractures in the rock. We wanted homogeneous crystalline rock. We're looking for granitic rock that was pretty large expanse of granite that we could work in and test technologies. And then, as I said, those specific conditions about permeability and stress as well. And the Utah site best fit those needs.
We've known about geothermal for a long time, and I want to stress this idea that Forge is really a real effort to unlock and explore the potential that geothermal could have in places that aren't exactly perfect for geothermal. Why do you think it's time now to take a real hard look at geothermal's potential? What's changed? Was there maybe like a technological barrier in the past? Why now?
Yeah, that's a great question. So hydrothermal, which is just essentially traditional geothermal where we have heat and permeability and fluid all together naturally. We've been producing geothermal energy from hydrothermal systems around the world for hundreds of years. In California, there's a massive resource in the geysers north of San Francisco. In Idaho, Nevada is a massive resource as well, which has a tremendous amount of production. Traditional geothermal has been operational and is very cost effective in these regions where we have these appropriate conditions for hydrothermal systems. And EGS is sort of this next frontier, as we described. Another new frontier for the U.S., which is a much more straightforward technology to tackle, is this direct use and geothermal heat pump area, which is not as much of an engineering and technical challenge. It's more of a trying to understand how to make this more efficient and then deploying it. But basically using relatively warm water to heat and cool your home or to heat and cool industrial centers or district systems like cities, which is widely used in Europe, becoming more and more utilized in Asia, and New Zealand. And this is something that the U.S. has a really significant opportunity to deploy. And so I think it just so happens, our vision study has given us some really exciting results to rally around, to maybe bring people's attention to the fact that hydrothermal exists and we're developing it, and it's cheap and it's clean. And it's now becoming a major contributor in California, where there are some issues in terms of dispatchable, having too many renewables that are non-base load on the grid. And then with the big prize of EGS, all of which is outlined in the vision results, where we could have 60 gigawatts by 2050 of geothermal energy on the grid, which is 8% of the generation of the U.S. in total. I think the vision has really given us an opportunity to sort of bring together all these pieces that might have been a little disparate before and help the community understand the values that geothermal can offer.
Yeah, you touched on this a little bit, what you've learned from Europe. Should we always think of geothermal energy as producing large-scale power? I think that's what we always think the end goal should be, but help us with our expectations. I think you mentioned this idea of maybe a smaller scale deployment of geothermal, especially when it comes to things like hot water, which we don't really think about too much.
Exactly. So you're exactly right. I was touching on this a second ago, in that the wide range of applications of geothermal, I think, are really compelling. Yes, we're starting from about 200 degrees Fahrenheit to some resources can be on the order of 700 degrees. We can produce electricity and power. And then when you get below that, we have new systems that you could put on the back of a truck, these little low temperature power production units that can produce power from around 150 C to 200, even a little bit lower. You can also, in that same range, use essentially hot water, no power production necessary, but for processing food. In Nevada, there's a little industry where they're drying onions adjacent to a hydrothermal plant. In New Zealand, they're drying milk and then shipping it all over the world. We can use it around 150 F down to around 60 to grow tomatoes in Alaska, which they're doing with geothermal water. So no power production. We're just using hot water, filtering it through a greenhouse to make the greenhouse warmer, and we're growing plants where you wouldn't normally be able to grow vegetables and plants. There's just this massive range of opportunities for geothermal outside of power production. We're very proud of the opportunities that we can present and the clean, renewable baseload power production that we can provide. But these other opportunities are pretty exciting and provide this menu of options for the American public.
Lauren, I feel like I hear a lot of criticisms about geothermal in that maybe the equipment isn't up to snuff, like the heat exchangers will wear out over time. Help us clarify some of those misconceptions if they are.
In general, I'd say that we have plants that have been operating for over 30 years in different parts of the U.S., Nevada and California. In Italy, where the first hydrothermal plant ever was created in Largarello, our surface equipment is actually quite efficient and long-term pretty sustainable. I would say that maybe there's some confusion because our reservoirs are hot and have entrained minerals that when they're in heated water are sort of flowing along in the water, but then when the water cools down, they might precipitate out. We sometimes have challenges with scaling, where we have the precipitation of materials that are clogging up our pipes or might be creating some issues. We do have challenges just inherent in the fact that we're working in a really deep, hot, and caustic environment that can create some challenges for our equipment. And to your question about Forge, I would say that we're definitely interested in Forge in trying to develop new methods for better understanding the subsurface in light of those challenging conditions that we work in. It can be hard to even, in some cases, measure where fluid is going in a well bore. You can imagine we have a well bore that's 10,000 to 12,000 feet deep. How would you know where fluid is going if your sensors can't function at the temperature that the bottom of that well bore is? We have a 400 degree Fahrenheit well, and our temperature sensor explodes. That can be a challenge, and that's something we are looking to address at Forge and through our R&D portfolio in general within the Geothermal Technologies Office, definitely.
You mentioned with EGS, you're introducing water into the system, you're drilling your own wells, you're not using natural fissures and things like that. So especially this issue with controlling the water that's going in, and you mentioned scaling and maybe the water naturally has minerals in it. If you can control the water through EGS, it seems like an EGS system would have a better chance of not scaling when you can control those factors.
Yeah, that's a fair point. Generally, though, what happens is as you're heating up rock, and the rock is already hot in the subsurface, that just creates more opportunity for minerals to precipitate out of the rock and into the fluid. We can control the water that we put in, you're absolutely right. In both hydrothermal and in EGS systems, we can make sure that we're injecting very clean water with nothing entrained in it that would gunk up our system. But what ends up happening is just inherent in the conditions of the reservoirs we're flowing through. Some of the minerals are coming out of the rock and pollution into the water. But this has been happening since the start of geothermal production, and there are a lot of very effective systems for reducing scale and for managing scale at the surface. But I would say that from an EGF perspective, you brought up a really good point in that for us, everything relies on these permeable pathways staying open to allow our fluid to transmit through the hot rock and bring that hot heat up to the surface. And so if some sort of chemical process happens where a mineral decides to precipitate and seal up a fracture, that's problematic for us. Another big challenge that we're trying to understand, I was kind of alluding to how to create these fracture networks and control our permeable pathways in the subsurface as a major challenge we're looking to address with Forge. The chemistry becomes a very significant piece of that, is how to understand where and when that might happen, and then how to mitigate if that does happen, so we can maintain these large, low surface area reservoirs that allow lots of fluid to be flowing through fractures. We don't want one big flowing fracture because we remove all the heat out of the rock really fast that way. So we want lots of dendritic fracture networks that can transport heat across a larger area.
According to your website, you discuss dynamic reservoir models. Are they different from the tools that, say, like oil and gas engineers have been using to characterize the geology? You'd think that industry knows just about everything that's going on underground. So what extra data do you need to know about the geology that the oil and gas industry doesn't track?
Sure. So I'm really glad you asked this question because modeling is an absolutely critical part of the Enhanced Geothermal Systems program, and I believe working in such a cutting-edge technology space. Basically, we use modeling everywhere to design our cars, to estimate what the weather is going to be like tomorrow, for medical research, to understand our physiology. And basically, there are sometimes things that we can't measure, and especially in our environment in the subsurface where it's challenging to measure things because of the heat and because of just the fact that some of them are inaccessible, or they might be too small to measure or happen really fast. Modeling is really important to be able to account for some of those things. Also, to do some predictive estimations of what might happen, considering how expensive it would be if you actually tried to do it in the field. So if you drill a well and you try to create a fracture network and then drill another well into the fracture network and it doesn't work, you've spent $10 million and that's that. Whereas you can spend maybe $100,000 at most and do some modeling and have a lot of different scenarios under which what conditions might make most sense. To your question regarding oil and gas, we are modeling similar things in oil and gas. We want to understand how the rocks are responding when we're injecting fluid into them. We're basically governed by the same relationships: conservation of mass, conservation of heat, Darcy's law, which is how hot water and steam are moving underground. And then we add our own data from every site that we work in, so the geological data and the hydrological data, to understand how a geothermal system might behave. The fundamental differences in oil and gas, in most cases, we're just trying to extract fluid in a massive quantity as much as we can out of the subsurface. For us, we are trying to engineer, and this is why I think this is such an exciting problem, engineer the rock to do what we want it to do, to transport fluid throughout it for a 30-year lifetime. So we really need to understand the mechanics of fracturing and the sustainability of fractures. So we're looking at models from a different perspective. Another big difference is that we're working in different rocks. We're working in crystalline rocks like granite, and the oil and gas industry are looking in a lot of the shale plays for gas. They're looking at shales, and those rocks respond really differently to fracturing conditions.
Is there cross-pollination with oil field? I know that Sue had mentioned they've done some technology transfers. For instance, there's a drill bit that DOE Geothermal had developed a while back, and the oil field uses it. At Forge, would we see a lot of people who came from the oil field sector? It's so crazy. It always seems like there's some sort of barrier up between power people and the oil and gas folks.
Yeah, absolutely. So I have a lot to say about that.
Go for it.
In terms of cross-pollination from geothermal to oil and gas and back, the polycrystalline diamond bit that Susan Ham, our office director, mentioned is an amazing example of research and development that came out of the geothermal office that's now used on a daily basis in the oil and gas industry. To your question about modeling, it just so happens we have another very notable example of geothermal transfer. Some of the TUF codes, which stands for Transport of Unsaturated Groundwater and Heat, it's a software code that was developed by Lawrence Berkeley Lab in the 1980s for geothermal reservoir engineering. And this kind of helps us model transport of water and vapor and gases in the subsurface and heat in fractures. This is definitely widely used across the subsurface energy industry, and it came out of funding from the DOE to Lawrence Berkeley Labs. We're really excited about that, and there is quite a bit of that cross-pollination happening in the technical space. I would say it's rare to say this because the oil and gas industry is incredibly technologically advanced, But in the space of modeling and the way that we're going about trying to create fracture networks, there's a lot of really interesting confluence of thinking between oil and gas and geothermal now, whereas previously tailored fracturing operations and customizing frac stages wasn't necessarily something that the oil and gas industry was interested in doing, and monitoring very closely and analyzing the data that is collected, because oftentimes there's a lot of data collected but it's not analyzed by the companies, to look at pressure, to look at where fluid is flowing, and to understand what their fractures are looking like, the length of fractures in the subsurface, are they behaving the same way, and how that translates into optimal well spacing and fracturing techniques for oil and gas. This is something we've been doing for a long time because we need to, because water, it's not that valuable compared to a barrel of oil. They're now trying to extract more efficiently oil and gas from the subsurface. The researchers in oil and gas are recognizing that, we really do need to understand how our fracture systems are behaving. We do need to model this. We do need to actually look at this data and be vigilant in actually collecting lots and lots of data. I think that this is an incredibly exciting time for geothermal because we have more opportunity to partner with the oil and gas industry, who has incredible expertise in lots of funding, lots of experience. The more data, the better. This is a great time, I think, for both industries, so we can bring what we've done in the past 10 years and 15 years in modeling, and they can bring what they've done and come together to try and better understand fracturing. Understanding rock and rock response in the subsurface is fundamentally the key to both oil and gas and geothermal energy for EGS. I'm very excited to hopefully see participation from oil and gas service companies or developers in general in Forge. The expertise couldn't be more perfectly applicable. These are reservoir engineers, geologists, exactly the same skill sets that are required in geothermal, and we need their help, and we would love to partner with them more. So there's hopefully an opportunity to do that.
Yeah, and for this podcast, one of the things that I've made a big point to do is do oil and gas stories and do power. It's all energy. Yeah. So who is out there? I've spoken to several DOE groups on the podcast before who've explained that a lot of the research is carried out by private businesses, universities, people awarded grants. It's not just people with DOE emails.
Oh, yeah, that's right. My job is designing the strategic direction of the Enhanced Geothermal Systems program, help deploy EGS commercially, so solve all the technical challenges to deploy commercially, and basically to give away money to technically capable people to do that work. We fund the U.S. National Laboratories to do this work. We fund academic institutions all over the U.S. We fund private industry, small businesses, pretty much everyone that meets the criteria of our funding requirements. We issue a funding opportunity announcement that we call it. Essentially, we're looking for research on this topic to meet these metrics, and then folks apply, and the best projects win. Yeah, we have a diverse community of folks involved from all over the U.S., and very lucky to have some institutional knowledge at some universities and our national labs that have been around for 15, 20 years working on geothermal problems and growing the interest in the community on geothermal. Yeah, we have a nice, diverse portfolio.
Very nice. All right, Lauren Boyd, Department of Energy, Enhanced Geothermal Systems Program Manager, thank you so much for your time.
It was a pleasure, Jay.
That was Lauren Boyd, Program Manager for Enhanced Geothermal Systems for the Department of Energy. From the Forge website, the team has wrapped Phase 2, or site characterization. They have now moved on to Phase 3, drilling and R&D. We wish them luck. I want to thank Lauren for her time, and another big thanks to Jerry Watson at the Geothermal Technologies Office for reaching out and setting this up. Also, thank you to John Horst in the Communications Department at DOE for his support. You can find plenty of pictures on Energy-Cast as well as on Instagram at Host Energy and Twitter at Host Energy Cast. All guests are sent the raw and completed audio the week of release. So far, no complaints. Be sure to leave us a positive review on iTunes. That gets the word out. Music was produced by Sean Stroop at Stroop Loops. That wraps up episode 83. Be sure to join us next week when we discuss how one company is keeping solar farms in the hands of their developers. Until then, I'm Jay Downhauer. We'll see you next time.